Section 11.9, representations of functions as power series. All right, so in the previous section, we talked about power series, which were series involving variables. Right, and then we found or determined for what values of the variable did the series converge or diverge. Now, one of the types of series that we know specifically convergence or divergence of is our geometric series. And we used other tests as well to determine convergence or divergence. But not only can we determine convergence or divergence of the geometric series based upon the R value, we can also tell you what it converges to, right? So what we're going to be interested in this section is taking a function and representing a function as a power series. Because one of the things that we talked about in that previous section, if you list the terms of a power series, because those terms involve a variable, because they involve x, right? We're only incrementing according to n, as n goes from 0 to infinity or 1 to infinity or what have you. Each of the terms of your power series is still going to be a function of a variable, right? So we ended up with a function, and very much they resembled a polynomial. Right? We made that kind of observation. Okay? So what we're after in this case is, can I take a function and represent that function as a power series? Right? So instead of going in the opposite direction. Now we're going to make use of our geometric series, because we know that geometric series converge for absolute value of r is less than 1. We also know that they converge to a over 1 minus r, right? So in this case, the first one, I'm looking at a geometric series with a equals 1 and r equals x. So I'm letting r be my variable, so x in this case. So that means that this series would converge for the absolute value of x less than 1. I have the power series sum as n goes from 0 to infinity of x to the n. And if you look at the terms of that series, when n equals 0, x to the 0 would be 1. And then plus x to the first, plus x squared, plus x cubed, etc., etc., etc. And again, we know that that series, because it is a geometric series, it converges to a over 1 minus r. A in this case is 1, remember our first term. And we've already said that x is r. So we know that this series converges to 1 over 1 minus x. That's our a over 1 minus r. Provided that r is less than 1, or absolute value of r is less than 1. So in this case, provided that the absolute value of x is less than 1. Okay. So then we have a way of representing this function. We'll just put this in function form. Call it f of x equals 1 minus x. As a power series, sum as n goes from 0 to infinity of x to the n. Okay? This has uses in mathematics in some cases, and I'll show you a couple of examples in this section where maybe I have a function that's difficult to find the antiderivative for if we're doing integration. Maybe expressing it as a power series, if possible, can make finding the antiderivative a little bit easier. Now you can also differentiate these things, right? So we'll talk about that as well. Differential equations, approximating functions with polynomials. All right, so notice even this function 1 over 1 minus x can be approximated by this polynomial function, 1 plus x squared plus x cubed. But remember, we talked about that polynomial having an infinite number of terms. That's one of the issues. All right, so how many terms do I need to use to give me an approximation of 1 over 1 minus x? Right? So again, that's the kind of thing that you can use this stuff for. Now, our objective, and this is the main part of this section that I'm interested in, is exactly that. Taking a function and representing it as a power series. Okay, now, again, we're going to make use of what we know about geometric series, because that's the ones we know the most about, at least in terms of easily being able to determine whether it converges or diverges. But also, we know that it converges to, and that's where the function is coming from. All right, so there's our a over 1 minus r. That actually ends up being our function. So here's the trick. Here's what we want. You want a function that can be written in the form of f of x equals 1 over 1 minus something. Right? And then whatever that something is, that's your r value. And so then I end up with this series, sum as n goes from 0 to infinity, of whatever that something is to the nth power. Right? That's our basic geometric series. It's r to the n. Okay? More generically, we always said a times r to the n or a times r to the n minus 1. But in this case, a is 1. Right? And so we have that sum, which is 1 over 1 minus r. So that's the trick. You want to take your function, express it in the form of 1 over 1 minus r, and then writing the power series is pretty straightforward from there. I mean, this ends up being a pretty straightforward process once you get the idea of how to manipulate the function. Now, of course, we're only scratching the surface here, right? We're only working with certain types of functions that fit a nice little format, but it gives you the idea of how this type of stuff is used or done. So, for example, let's take the function f of x equals 3 over 1 minus x to the fourth. I want to represent that as the sum of a power series. We also want to find its interval of convergence. So I was talking about interval of convergence, radius of convergence, that type of thing. Now, since I want this in the form of 1 over 1 minus something, that numerator, which is 3, let's pull it off. Right? Let's rewrite that as 3 times 1 over 1 minus x to the fourth. And then that's exactly what we need, because there's our something. Right? Now, again, this is the part that I'm representing as the power series, 1 over 1 minus x to the fourth in this case. That times 3, well, that's just 3 times that power series. And that's just a constant. So 3 times 1 over 1 minus x to the fourth. Now, again, whatever that r is, whatever that something is, that gets plugged into our power series to the nth power. There's our geometric series with r equal to x to the fourth. And I just have 3 times that sum, as in goes from 0 to infinity. Because, again, remember, we want the first term to be 1. So if I raise x to the fourth to the 0 power, just like anything else, I get 1. So I've got 3 times the sum, as in goes from 0 to infinity of x to the fourth to the nth, or 3 times the sum, as in goes from 0 to infinity of x to the 4n, which is a geometric series with r equals x to the fourth. And so we know it converges then again for r, absolute value of r less than 1. So in this case, absolute value of x to the fourth less than 1, or simply x to the fourth, because that's always positive. But either way, take the fourth root, and you still get absolute value of x less than 1. Right? So our interval of convergence is still negative 1 to 1. Right? Now remember, this is a geometric series, so you don't have to test the endpoints when we talked about interval of convergence. The radius of convergence is one thing. Right, the radius of convergence in this case would be 1. Our interval of convergence, we have to check those endpoints to see if we have convergence or not, remember? But again, in this case, it's all based upon a geometric series, so I know this only converges if the absolute value of r is less than 1. So I don't have to check the endpoints in this case. Next one, express the function f of x equals x squared over 8 minus x cubed as a power, or sum of a power series. Right, so kick it up a notch. Find our interval of convergence. Now, f of x equals x squared over 8 minus x cubed. We want a function of the form of 1 over 1 minus something. Now again, I said automatically your first step, just pull off the numerator. Rewrite it, in this case as x squared times 1 over 8 minus x cubed. Now I need that denominator to be 1 minus something. So I want this to be 1. And if I want that to be 1, let's just factor out whatever's there. So I'm going to factor that 8 out of my denominator. Now, that'll of course turn that first term to 1. The second term, though, would then have to be written as x cubed over 8. So that if you redistributed that 8 back into that denominator, you would get 8 minus x cubed. But again, that's pretty straightforward, right? I'm just pulling off, I'm factoring out whatever that constant is. And then our second term is simply then divided by that constant. All right, but again, it's a pretty straightforward little pattern, little formula if you wish. So I've got x squared over 8 times 1 over 1 minus x cubed over 8. So this is what we want in terms of our function f of x. That's going to be our power series with r equal to x cubed over 8. Now notice the x squared over 8. That doesn't depend upon n. right? So I mean, if I have x squared over 8 times 1 over 1 minus x cubed over 8, the power series sum as n goes from 0 to infinity of r to the n, so x cubed over 8 to the n, times whatever this is, because that doesn't require or involve n. So I've got x squared over 8 times the sum as n goes from 0 to infinity of x cubed over 8 to the n. And again, that's really all there is to it. The rest of it is just rewriting. So that'll give us x squared over 8 times the sum as n goes from 0 to infinity of x to the 3n over 8 to the n. And then I'm just bringing back in the x squared over 8 into our series. So I'm just redistributing what I originally pulled out. So that'll give me x to the 3n times x squared, which is x to the 3n plus 2. That'll give me 8 to the nth times 8, which would give me 8 to the n plus 1. Right, so here would be a nicer version of our power series. Right, so this is what I'm ultimately interested in as the final version of our power series. Now, interval of convergence. Now, right, what was r in this case? R was x cubed over 8. There's my r. And so we know we have convergence when x cubed over 8, or its absolute value, is less than 1. So there's our absolute value of x cubed over 8 less than 1, which gives me absolute value of x cubed less than 8, just multiplying by 8 on both sides. Which means x cubed would have to be between negative 8 and 8, or x would be between negative 2 and 2. So our interval of convergence, negative 2 to 2. Now again, these can be differentiated and integrated. Differentiation and integration with these. I'm going to show you how this works. Like I said, I'm really just mainly interested in what I just showed you in terms of just being able to take a simple little function and express it in the form of a power series. But like I said, we're just relying upon those that are written or can be expressed in the term of a geometric series, because that's the easiest to work with. But you can differentiate and integrate these things. The sum of a power series is a function, right? So f of x is sum as n goes from 0 to infinity. Now remember our general form of a power series. It was that sum as n goes from 0 to infinity of c sub n times x minus a to the n, where we called it a power series about a, or a power series in a, where the domain was our interval of convergence, right? So whatever values of of x the series converged, right? Our interval of convergence was in the domain of our function. Okay. Now, to differentiate and integrate, let's look at this initially term by term. Right? So if we write out the terms of our series, and then we follow our basic processes for differentiation and integration, which again, since these resemble polynomials, it's really going to be an application of power rule. We have a theorem that tells us that if the power series sum as n goes from 0 to infinity of c sub n x minus a to the n has a radius of convergence r greater than 0, so it actually converges for some values, then the function f defined by f of x equals c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared, etc. Remember, that's just taking our power series, plugging in values for n starting from 0 to infinity. So c sub 0 would be our first times x minus a to the 0, which is 1. So our first term is c sub 0 plus c sub 1 x minus a to the first plus c sub 2 x minus a squared, etc. Right, our sum as n goes from 0 to infinity of c sub n x minus a to the n. It is differentiable and therefore continuous. And maybe a quick reminder on that. Remember way back when we talk about differentiability and continuity. Differentiability guarantees continuity because you have to be continuous in order to be able to differentiate. But continuity doesn't guarantee differentiation. Right? Now, that's not going to be a big portion of what I'm interested in, but just as a reminder, if it is differentiable, then it is continuous. And it's going to be on the interval from a minus r to a plus r, right? Because again, r is our radius of convergence. It's a radius of convergence about a, whatever that a value is, right? And so we have an interval of convergence from a minus r to a plus r. And then whether or not we include the endpoints is a matter of checking. Now, differentiation. If I look at f of x as that sum of n goes from 0 to infinity of c sub n x minus a to the n, so I'm referencing this, and I differentiate that term by term. And so I take our first term, which is c sub 0. Well, that's just a constant, right? So the derivative of c sub 0 is 0. What's the derivative of c sub 1 x minus a? Again, we can just use basic power rule. It's x minus a to the first. Power rule, chain rule, if you wish. So it's 1 times c sub 1 times x minus a to the 0, which x minus a to the 0 is 1. So I'm left with just c sub 1. The rest of it is a little more straightforward, a little more obvious, I think. This power rule, 2 times c sub 2 times x minus a to the first. So then 3 times c sub 3 times x minus a squared, etc., etc., etc. So we lose the c sub 0 because c sub 0, like I said, is a constant and its derivative would be 0. And so I end up with the series as the sum as n goes from 1 to infinity, because notice our first term of f prime is c sub 1, plus 2 times c sub 2 x minus a to the first. So let's go n times c sub n x minus a to the n minus 1, right? But that's nothing more than what? Our basic power rule for power functions, right? Which is what this is. It's what it resembles. So it's simply then the sum as n goes from 1 to infinity, n times c sub n x minus a to the n minus 1, basic power rule. Integration. It's going to work the same way, right? Just in the opposite direction, obviously. So if I take the integral of f of x dx, where f of x is our sum as n goes from 0 to infinity, c sub n x minus a to the n, our power series. And again, we go term by term. Now ignore the plus c for a second. But the first term, all right, if we take c sub 0, what is the antiderivative of a constant? Well, it's the constant times x. Well, in this case, it's the constant times x minus a, because this is a power series in form of x minus a to the first, all right, divided by 1. Our next term would be c sub 1 x minus a, so its antiderivative would be c sub 1 x minus a squared over 2. All right, power rule. Raise the exponent, divide by the new exponent, plus c sub 2 x minus a cubed over 3. Raise the exponent, divide by the new exponent. And then, of course, whenever we do an indefinite integral, a general antiderivative, we always tack on the plus c, right? So that's where this guy comes from. Put it in front, put it in the back. What's the difference? It's just a term of the series. So in this case, we're putting it in the front. It just looks a little nicer, but you could just as easily write it at the back end, as we always do. But I'm looking at this part. Here's your power series. Sum as n goes from 0 to infinity of c sub n x minus a to the n plus 1 over n plus 1. Right? Again, that's just our basic power rule. Right? It's the constant times the variable raised to a higher degree, increased by 1, and you divide by the new exponent. And then we always tack on our plus c because, again, it's an indefinite integral. The radius of convergence of the power series, whether you're differentiating or integrating, is still r. Right, so whatever the radius of convergence is for your series, the radius of convergence for its derivative and its integral are the same. Now, the integral of convergence may change. I'll mention that in a second, right? Because remember, we still have to check those endpoints, because even though we have a power series that's originally a geometric series, right, we know it converges for absolute value of r less than 1. Once we find its derivative or its antiderivative, now we've changed that. Right? And so once we determine what the radius of convergence is, we still may then have to check those endpoints. And again, I'm not going to make that as big of an issue right now. I'm going to be interested in the radius of convergence. Notation at the bottom. Just note before we go further. that the derivative of a sum can be written as a sum of a derivative. Integral of a sum can also be written as the sum of an integral. And if you want the proof of that, as always, like I tell you, read the book. Right? But we'll just take that as equivalent notation. And then this is what I said earlier. Right? The radius of convergence remains the same. The integral of convergence may change, right? Because I always say with these, you have to check your endpoints depending upon the type of series that you are, or the type of test that you're using to determine convergence or divergence. In the case of a geometric series, we know its absolute value of r is less than 1. We don't have to bother with the endpoints. But if we have to use some other test, like a ratio test was very common to determine convergence, then we have to check those endpoints. All right, so for example, I want to at least give you an example of each one. Like I said, I just want to show you how these work on your final. I'm just going to ask you to represent a function as a power series. I'm not going to ask you about derivatives or integrals on the final, but just to give you an example of how these guys work. So let's say, for example, I want to find a power series representation for the function f of x equals natural log of x plus 1, right? That's not a function that I can put in the form of 1 over 1 minus something. But what is the derivative of ln of x plus 1? Remember, our derivative of the natural log is 1 of the argument times the derivative of the argument. So in this case, the derivative of ln of x plus 1 is simply 1 over x plus 1. That's f prime. So if f prime is 1 over x plus 1, then the ln of x plus 1 is the antiderivative of that, right? So I could represent ln of x plus 1 as the integral of 1 over x plus 1 dx. Now, once I have that function here, I can recognize again, I can represent that or write it in the form of 1 over 1 minus something. So this may be a part I would be interested in terms of the power series itself. So 1 over x plus 1 can be written in the form of 1 over 1 minus something. Specifically, it's 1 over 1 minus the opposite of x. And so there's our power series with r equal to the opposite of x. And so that one's actually pretty straightforward. So I've got then the integral of the sum as n goes from 0 to infinity of negative x, or opposite of x, to the n dx, whose antiderivative then, using our, like I said, our basic power rule, there's our plus c, times the sum as n goes from 0 to infinity of opposite of x raised to the n plus 1 over n plus 1. All right? Basic power rule. Now, after that, it's rewriting. I mean, there's nothing wrong with this in terms of the power series itself. But since we are interested in interval of convergence, we may need to rewrite that into a form that would make it easier to determine that, right? But again, in terms of the series itself, if that's all we're interested in, give me a power series representation, that's a perfectly good series. I mean, there's nothing wrong with that. But underneath that, we rewrote it, first of all, as c plus the sum as n goes from 0 to infinity of negative 1 to the n plus 1 times x to the n plus 1 over n plus 1. So just put off the negative 1 as a separate factor. But then notice if n equals 0 in this series, with n equals 0, that would be negative 1 to the 0, which is negative 1 to the first, or negative 1, times x to the 0 plus 1, or x to the first, over 0 plus 1, or 1. So I get negative 1 times x as my first term. Well, that would be exactly the same first term if we just manipulated our index a little bit, and instead of going from 0 to infinity, let's start our series at 1, and let's change the exponent from n plus 1 to n. So notice this series. With n equals 1, that would give me negative 1 to the first times x to the first over 1, which would be the same first term that I would get with the previous series. All right, now again, either one of those is a perfectly good representation of the same series. We've talked about before, you can manipulate those indexes to start wherever you want it to start. And the second one is a little more convenient than the first. It's a little nicer, right? But especially in this case, since we're interested in finding our radius of convergence, and making use of the ratio test. Okay? So again, either one of those is a perfectly good representation. Actually, all three, because like I said, the first one that I have here was perfectly good, and then the other two are just rewritings of that. But if you don't rewrite it the way that I just did, you could still use your ratio test, and instead of n plus 1, your ace of n plus 1 would be n plus 2. Right? It would just make it a little bit more difficult to do the ratio test. But again, I'm running it through ratio test to find our interval of our radius of convergence. Right? So I've got the limit is in approach to infinity, ace of n plus 1 over ace of n. So x of n plus 1 over n plus 1 over x to the n over n, or times n over x to the n. Now again, absolute value. Right, so I don't have to worry about the negative 1. Actually, I left it out when I wrote it. Okay. So I got the limit as n approaches infinity. Now again, the x of n plus x to the n plus 1. Now how many mistakes did I see made? X to the n plus 1, right, is x to the n times x. So I can divide out the x to the n, and leaves me with x times n over n plus 1, and absolute value of x, and we have to keep the absolute value there because x is a variable, times n over n plus 1, which we know as n goes to infinity, this approaches 1. We've done that enough times by now, we should know that. So that this limit would be equal to absolute value of x. Now again, we know that this converges when absolute value of x is less than 1. Why? Because this is ratio test. Right? And we said the series converges if its absolute value, if the limit, I should say, is less than 1. Right? And so our limit in this case is absolute value of x, so it converges when that is less than 1, or x between negative 1 and 1. There's our r of 1, radius of convergence. Right? The second one, just to give you an example with integration, or how you can use integration as well, or, excuse me, derivatives as well. That's a lot trickier because, and again, it depends on the function. I mean, this one was a little bit straightforward because I could recognize easily enough that the derivative of ln of x plus 1 is 1 over x plus 1. And then boom, I have a function of the form that we wanted, the 1 over 1 minus x. This is a little bit more problematic. So expressing the function 5 over 1 minus x squared as a power series, find the radius of convergence. But here you'd have to kind of recognize that, hey, obviously 5 over 1 minus x squared is the derivative of negative 5 over 1 minus x. We all could recognize that easily enough, right? No. But with that said, since 5 over 1 minus x squared is the derivative of negative 5 over 1 minus x, then that's what I'm going to start with. Let's start with the derivative of negative 5 over 1 minus x. Now here we're back to business as usual. This is straightforward from this point forward. All right, and I'm going to represent that as a power series. So again, I'm pulling off the constant, the numerator. Right? Anytime you're converting to a power series, I want 1 over 1 minus something. So pull off the numerator. So negative 5 times the derivative of 1 over 1 minus x. Well, heck, that's exactly what we want. So there's our 1 over 1 minus something. Our something in this case is just x. That's my r. So there's the negative 5 that we pulled off times the derivative of the sum as n goes from 0 to infinity of x to the n. So negative 5 times the sum is, or negative 5, I should say, times the sum as n goes from 1 to infinity of n times x to the n minus 1. And so our integral, just using our power rule, increase there, multiply by the exponent, and decrease the exponent. So our derivative of x to the n would be n times x to the n minus 1. Now again, notice, remember we said with the derivatives, you lose the first term, you lose n equals 0, because the first term of your series here, right, is x to the 0, which is 1, whose derivative is 0. All right, so when you are differentiating these guys, if you're starting at 0, these power series, these geometric series, you lose the first term. And so your increment starts at, or your index starts at 1. All right. All right, so there's our new power series. Again, radius of convergence there is still 1, because that's still just nothing more than a geometric series, right? That's n times x is n minus 1. Still a common geometric series. But like I said, just to give you an example of how those work, I'm not going to be interested in that for your final. What I am interested in is, here is a function. Let's represent that function as a power series. That's what I'm going to ask you to do. Okay, but it gives you a little bit to look at for that section.